Hi, we are Team Seascan, and our project is the Vacuum and Temperature Monitoring Sensor, or VTMS for short. Our technical directors are Richard Arthur and Peter Jones, and our consulting technical director is Mike Smith, a URI graduate. I am Chris Alexander, an electrical engineering student. With me is Michaela Belisle, also electrical engineering, and Mariah Messenger, computer engineering. Seascan is a small company located in Falmouth, Massachusetts that manufactures oceanographic instrumentation and equipment to be used primarily in scientific research development. They create a number of pressure-tolerant enclosures, which is our main focus for this project. Shown here are two examples of pressure-tolerant enclosures Seascan manufactures. The pressure housings are used to protect electronic equipment and battery packs when submerged in water. Once fabricated, Seascan will pull a vacuum of the housing and monitor it for 12 to 24 hours as a pretest to ensure it is functioning properly. The pressure housing is then sent to the customer. However, they will have no way of knowing if it is properly sealed after opening and closing the housing. This project is driven by the need to guarantee the enclosure is sealed every time it goes into the water once it is in the hands of the customer. The anticipated best outcome is a functional prototype that can monitor vacuum, temperature, and humidity levels and report the status to the user. A GUI application will be created to display sensor data and accept user inputs. The system needs to be able to send and receive data between the main circuit and GUI application via Bluetooth or Wi-Fi connection. A system user manual describing the hardware and software components will accompany the prototype, along with test results and a demonstration of the working system. We are pleased to say we met our anticipated best outcome. Seascan's pressure-tolerant enclosures are essential for oceanographic research, and the ability to ensure their performance is even more crucial. As the company seeks to expand the market of their products, they will need to meet the demand for monitoring and collecting data from these enclosures. The first and most substantial step towards doing so will be developing the VTMS and a complementary application to it. This would ultimately improve the product's reliability, longevity, and increase its value. This is the block diagram of our proposed system. It shows the components to be included in the main circuit and how it will interact with the GUI application. We will discuss further on the different aspects shown in the diagram. The program used on designing the schematics was CircuitMaker. It allowed us to map out connections between other components that will be placed on the boards. One of the main components on the PCB is the ESP32. The ESP32 is the microcontroller that handles all the computing on the board. For testing purposes, two different versions were used to compare their positives and negatives to choose which would be best in the end. This project is operated by a 5-volt battery and as a result needs to be power efficient to preserve the battery life. A load switch is used to power everything from one of 3 triggers: the read switch, the external real-time clock, and the ESP32. With this method, the ESP32 is able to wake up from an external source easily and keep itself on through the load switch. There are many components on the PCB that deal with information on and off the board. The BME280 collects all the data, the LEDs portray messages to the users as well as display the data, the microSD stores the data, and several connectors transmit signals like serial data to and from the board. Another function of the CircuitMaker program is to design the custom PCBs. Like the schematic, the purpose of this is to physically map out where all the components go and their connections to all the other components on the board, as well as add anything to the board that will be necessary to make these connections. Mariah Messenger will now discuss the software aspects of the project.
To meet the software requirements for our project, we needed to build an application that allowed the user to interact with our hardware from a Windows 10 computer. This meant we needed to create a graphical user interface and establish communication with the hardware through Bluetooth. To develop the graphical user interface, a Python module called Tkinter was used. And to develop the Bluetooth low-energy communication portion of the software, a Python module called Bleak was used, based on its compatibility with our project requirements. Both the graphical user interface and BLE portions of our software are incorporated into one Python file and made to interact with one another. Anytime the user requests to connect, disconnect, or send operation parameters to a device by clicking a button, specific Bluetooth Low Energy processes are called, and our software is also able to process any received data to display it in the GUI. Although the relationship between the graphical user interface and BLE sounds simple, it was surprisingly complicated to implement. Each part of the program is performed asynchronously, so the question was, how do you keep the graphical user interface from freezing while a BLE function executes? The solution to this problem was using another Python module called async.io to create coroutines. These coroutines can be called in a way that allows one coroutine to run while the software is waiting for another to finish. Thus, they run asynchronously but do not halt other processes. Our software runs from a standalone executable file that writes to the directory C users public documents VTMS on the user's computer. If this directory does not exist, it is first created. As you can see here, the folder VTMS does not exist in this location on the user's computer initially. Once we run the application, the device information page will appear. However, in order to apply any of these settings to a device, it needs to be connected first. To do this, the user can click on Devices, then Connect Device to bring up a new window that will walk them through the connection process. The software first scans for any BLE devices, then displays their MAC addresses to the user. Once the user selects the device they want to connect to, the software will try to connect to it and notify them once the device is connected. From here, the user can send any device parameters by clicking the Apply Settings button and will be notified once that information has been sent. Since the application has been run, the directory where it will store data has now been created. The CSV file BLE data will contain all of the data, and this file format was chosen so that the user may also open this file in Excel and take advantage of any Excel functionalities. Once the user clicks Get Data in the View Data page, the software will read the data from the CSV file and display it accordingly. This list will be updated with any new data anytime the user clicks the button, and a scroll bar was placed on the side to navigate through large amounts of data. Once the user is finished using the device, they can disconnect from it, which will stop any BLE processes from running. To continue our presentation, Michaela Belisle will discuss the firmware developed for the system.
The firmware was developed using the Arduino IDE for the ESP32 and peripherals mentioned earlier. Upon powering on, everything will be initialized except for the real-time clock, also referred to as the RTC. The system will then check to see if it has been previously set up by the user. If it has not been set up yet, the LEDs will blink red until data is received from the graphical user interface. Once received, each parameter will be extracted from the string of data, and the corresponding variables will be set to be used by the firmware. The information will also be stored on the flash memory to be recalled upon next power-up sequence. Once this has been done, the RTC will be initialized with the current date and time sent by the user. On the other hand, if the system has been set up already, the parameters will be read from the flash memory and the corresponding variables will be set. After each of these scenarios, the RTC alarm will be initialized to allow the circuit to be powered back on after a user-defined amount of time. Next, the system will run through a loop for the user-defined number of samples, referred to as data num. The counter I will be incremented each time to keep track of how many times the loop has run. During this loop, sensor readings are taken, stored on the microSD card, and printed to the serial port. The system will then check for a BLE connection. If there is no connection, an LED sequence will be initiated to show whether or not each sensor value is within the user-defined range. The LED will be green if it is within the range, blue for below, and red for above. If there is a BLE connection, there will be one white LED to indicate this, and the data will be transmitted to the BLE client. After either of these scenarios, there will be a delay defined by the user as the data collection frequency. Additionally, all LEDs will be turned off. If the counter I is greater than data num, the system will check for a BLE connection again, and if there is one, the system will stay powered on and continue transmitting data to the BLE client. If there is no connection, the RTC timer wake-up will be set and the system will power down. The system will power back on after the user-defined sleep time, or if the user swipes a magnet by the read switch. Then this whole process will be repeated. Prototype testing was performed with the populated PCB and firmware. First, you can see the LEDs indicating that the system has not been set up yet. Next, we have the power on sequence of a system that has been set up. The blue LEDs indicate that the parameters are being read from the flash memory. The system is now running through the loop, and as you can see, all of the sensor values are within range. There will then be a red, green, blue LED sequence before the system powers down. Lastly, you can see what happens when a BLE connection is made. By combining the electronics, software, and firmware, we were able to create a functional prototype shown above and ultimately reach our anticipated best outcome. And with that, we would like to extend a big thank you to our technical directors and consulting technical director, Richard Arthur, Peter Jones, and Mike Smith, who gave us guidance and support throughout the project. And last but certainly not least, we would like to thank our Capstone Program Director, Dr. Harish Sunak, for his countless effort and passion he dedicated to make this program possible.